Good morning, afternoon, evening, scholars, whenever you're watching this video. We are picking up with, I would say, an extension lesson of our previous content from the last activity, where we spent some time looking at how to define the midline and amplitude of a trigonometric function. If you weren't able to get to that video, the midline is known to be the horizontal line that effectively cuts a trigonometric function in half. Algebraically, it is the constant in the trigonometric expression. Well, some really gnarly indigestion. The amplitude is the distance between the maximum or minimum values, since they are opposite one another, and its distance to the midline. That value is typically identified as the coefficient of sine, or in other words, the scale factor of the function. This lesson is going to focus on the horizontal translation of a periodic function, and if you remember back to the time or our unit on back to our unit on transforming functions, this would be when we are modifying the input value, or in this case, the theta value. So for the card sort, this is just designed to kind of revitalize your memory. As you can see, we have a regular parabolic function, two algebraic functions that are being translated left and rightwards. So take a look at what the behaviors are, see if you're able to jog your memory. But in this case, right, we have the blades of the windmill expend 4 meters from the center, and the center is 20 meters off the ground. The windmill rotates counterclockwise. So we're just going to write an equation here to represent the height once again as a function of an angle theta of rotation. So very similar to what we were doing last lesson. After you submit your response, explain your thinking. And as you can see, nothing here is necessarily new. In terms of the algebraic structure, you're simply tasked with describing your own windmill scenario based on the components and structure provided to you. So for this particular slide, we need to make a slight adjustment, okay? And unfortunately, there's overload here regarding the questions. But we have a fan here with radius 1 foot. A point P is starting out slightly rotated from our typical starting location. Right, it's at the pi/6 position on the circle. The fan turns in a counterclockwise direction. How does this graph compare to the graph of cosine of theta? And sketch a graph of the horizontal position h in feet of p as a function of the angle rotation theta of the fan from its starting position. Right, so notice the starting position is here, right? So at an input of 0, we are at a height, since the center is 0, 0, of whatever that corresponding value is for pi/6. That is a height of 1/2, right? And then you'll need to adjust your graph accordingly, but you should hopefully be realizing that all we are simply doing is modifying the horizontal location of our function. Slide 6 is asking you to sketch a graph of the vertical position v in feet of p as a function of the angle rotation theta of the fan. Oh, sorry, this was horizontal position. So this 1/2 corresponds to the vertical position, okay? Horizontal position at pi/6 is √3/2, which I think is like 0.8 something. So it should be slightly up here. All right, and then here we're doing the vertical position, which corresponds to sine of theta. And that is ultimately where we're going to pause, and we're going to pick up with a whole class discussion on how we could possibly construct an equation, or how we can create an equation that represents this type of contextual adjustment.